see if I can find that. There it is. It's hiding. So let's get this out of the way. All right, so up and running. Let's get the hair straightened out here. There's the old cowlick from Spanky and our gang. Doesn't matter. Let's keep it there. All right, so been thinking about the chain rule again, and actually had a very different perspective on it now the more I think about it. So I'm going to talk about it and hopefully make some sense for those of you who are just beginning to study the chain rule, and also for those who might be teaching it, some ideas on maybe a different way to do it. So the chain rule is pretty mechanical. I think that's how it's taught. So if you had 5 cosine of 4, 3 tan x minus 2x, you know, you do 4 times 5 cosine of this. I mean, not telling you anything you don't know here. All right, but I'm not sure that kind of, and I didn't even finish it off, did I, at the end? Yeah, I should have finished it off, but anyway. So that's the kind of thing I see in final exams, and you know, people get it right, some don't. But what's the understanding behind it? That's the hard part. Understanding and seeing what's going on. So I thought I'd try to just give some ideas on things that someone might say to be helpful. And so I'm getting a feel for it. All right, I did do a video, chain rule. Looks like something got erased here. Chain rule through the lens of integration. Kind of heavy stuff, I think, but I think it really is important to look at that. You know, when you take a derivative and integral of the functions on the upper and lower limits, I think this gets at what's going on. So I think that's really important. But if you're doing a sequential class, you're certainly not going to look at the chain rule through integration. So what helps there? Well, I took a pretty simple, I hope, fairly simple approach here. Looking at y equals parentheses 2x plus 1 cubed. And that's actually a perfect cube. 2x plus 1, 2x plus 1, 2x plus 1. And if you look at the video completing the cube, then you'll recognize that minus 1/2 is where the point of inflection is. And if you look at the completing the cube video, that will be explained as to why. So I think there's a geometric component here. 2x plus 1 is inside the parentheses. So, well, let's just look at that whole business I was talking about in terms of point of inflection for just briefly. So cubics can be drawn. Perfect cubes can be drawn pretty easily. And we can look at change, you know, minus 3 cubed, minus 27, minus 2 cubed, minus 8. So change from minus 27 to minus 8, I guess, is going up at 19 to 1, minus 8 to negative 1, 7 to 1, minus 1 to 0, 1 to 1. At 0, there's no volume. There's no volume. And I was going to bring in some Post-its. So how would this change? Well, it's 3 squares, right? The derivative of the cubic is the 3 squares. So it's kind of like painting those 3 squares on the box, and whatever, however much paint you use, the volume of the paint you use is really the rate at which this is changing at any instant. But when you don't have a box, you know, there's a big difference. I think it did it over here. There's a big difference squaring and cubing. Let's look at the cubing. I think that's what I was talking about. So when there's no box, 0 side lengths, and there's no volume. And if you change by 0.001, well, then you change over here by 9 decimal places with a 1. It's not much change going to happen there, not much. But if you went from 3 to 27, and I don't need a calculator for this, I don't think, except I haven't looked at this in a while. I think that number is 3 times the side length, right? So if you did 3.001, you've got your 3x squared, you know, 3 squared 9 times 3, there's your 27, 3 times the side length, and then it ends in 1. And we can see that, you know, the change 0.001 into 0.027, you know, fits the derivative of x cubed, which is 3x squared. It should be looked at geometrically. Those shapes should be drawn. So there's significant change here compared to here. And when we look at the cubic, you know, point of inflection right there. Why? There's no box. Why? It's a perfect cube. And if you've got a cube that has different dimensions, completing the cube gets that, you know, well, I'm not going to do it again. I just encourage you to look at the completing the cube video, and it spells out why that's happening. X squared, same principle with X squared. Did I put the boxes somewhere? Thought I did. You know, so you got your 9 units from -3, and then you got your 4, and then you got your 1, and then you got your 0, and then you got your 1, and then you got your 4, and then you got your 9. You know, there's change here, there's change, but it's getting smaller and smaller and smaller until there's no box, no square. All right, so again, same situation, 3.001, that's 9.006,001, and you should look at that relationship. It's not accidental, right? It comes from the geometry, of a 3 by 3, changing by 0.01, which I have to draw, right? I have to draw it, but it's really small, very small change, so it's like layering. So here you got 0.001 times 3, and here you got 0.001 times 3, and there's your 0.003, and there's your 0.003, and now you can start to see where that's coming from. And this here, this area here is 0.001. 0.001 times 0.001. You ignored that, right? That's the limiting process. All right, so I'm babbling a little bit, but gonna get to my point soon. So what do we have here? So the completing the cube video is worth looking at. And that takes ax cubed, bx squared, cx plus d, and reshapes it into your ax minus h cubed plus m x minus h plus k. So I encourage you to see the completing the cube video, but just looking at cubics, if the a, b, c, and d terms are positive, you know, it's point of inflection at 0. Oh, what am I doing? Oh, I'm looking at each term. I forgot what I wrote here a while ago. So and what I was just saying, let's go back to this. So here's your cubic, here's your quadratic, here's your linear, here's your constant. Hope that everything can be seen. Let me move this. All right, so you know, to come at the chain rule, I think it's good to come at it geometrically, numerically, and graphically. So we're coming at it graphically right now. Now let's talk about rates. The chain rule is all about finding rates of change. So at zero, I don't think that's changing much. In fact, it's not changing at all. If there's no cube, there's no change. Squaring at 0, you know, and you talk about why that graph is somewhat flat there, zoom in and it looks flat, but again, no box, no change. Linear, there's change. Constants, I don't think that constant's changing, and if you think it is, give me a call. We'll get you some help. All right, so if you put them all together, where's the change coming from? Coming from the linear term. Okay, so this function should be going up at whatever rate that is. That tells you something about y-intercepts, doesn't it? That y-intercept is going to be that, and how it's changing at the y-intercept is going to come from the linear term. All right, so now where are we? I think I talked about that over there. All right, so let's get to the chain. Let's go over here and what I think you should do with it to have it make some sense to you or your class. What will we do? We put a number in. We put a number like 1 in. 2 times 1 is 1, plus 1 is 3, and 3 cubes 27. Okay, and then we change it to 1.001, and I should have done that one out. I can't do that one in my head because I'm doubling it, and I only know the pattern when I'm doing, you know, basic cubing. So let's see, where do I want to go with this? Up. So how do we establish the rate of change here? Well, I think we should follow the same rules of order of operations here. Do the parentheses first, the 2x plus 1 first, and then, you know, at whatever value you want to, you know, I said at 1, then you've got to look at how things are, the cubic process is changing, but not at 1, at 3. Okay, so I think I did that over here a little bit. And what's the change like? Well, we're going to change from 1 to 1.001, but in the parentheses, that's a change of 3 to 3.002. Okay, and we can see that this changes by 0.002, and the x is changed by 0.001, and there's your 2 to 1. And all that does is reinforce what kids study at Algebra 1. All right, so, you know, this part of the calculus is just like a little microscope zooming in, small little changes. All right, so I want to mention that. And then we've got the cubic process, we know, is, you know, painting three sides, which are three squares of a perfect cube. And so we want to look at how that changes from 3 to 3.002 squared now. All right, and I get this value, which I couldn't have done without a calculator. And it turns out that it has this change. And because it's a, you know, it's an approximation. So nothing's going to be exact here, but, you know, if we look at this, and this has got a lot more decimal places, right? If I'm cubing this. So this is misleading here to a certain extent, but I'm betting that 54 is where that decimal will cut off. I didn't do it. I should have probably done it before, but guessing that's what's going to happen. All right, so that's a 54 to 2 ratio. And if we're going to multiply, chain rule is multiplication. Well, the 2's are going to cancel and you're going to get 54 for the rate of change of this function. Now, what's the way that this function would have been done in a typical classroom? 3 times 2x plus 1 squared times 2. And that reads nicely. And I think if we put a 1 in here, if we don't get 54, I'm going to probably have to stop the video. 2 plus 1, 3 squared, 9, 27, 2, it's 54. So that, you know, the numbers get crunched and they work out. But I'm suggesting that you do it in the order of 2 times 3 to the 2x plus 1 squared, and students might have a little better chance at following the numerics. All right, so now where am I going? Well, let's go, since it's a calculus class, let's actually multiply out. This is a babbling video, but I think some interesting things. So I multiplied 2x plus 1 cubed because I teach holistically, which means I want to hit some other topics while doing this. And so if you multiply it out, I like to do binomial squaring a lot with my students. We get this. All right, and a moment ago I said -1/2 was where there's no volume of the cube. All right, so if I wanted to find, without calculus, the x value of the point of inflection, then I'm going to do minus b over 3a. Minus b is minus 12. Yeah, I did it here. And 3 times 8 is 24. So minus 12 over 24. My God, yeah, that's -1/2. And -1/2 here, 0 cubed, no volume. So that's where this function is changing the least quickly. And you could have done the derivatives here, right? So here's your second derivative, 48x plus 24. We can see that at -1/2, you know, we get 0 and it changes signs there. So we're changing concavity. We've also got a quadratic, you know, that has a minimum value, right? So this thing has a minimum value at, and remember what the first derivative looks at, rates of change. So the minimum rate of change is when there's no volume, right? And quadratics have a minimum at the vertex. And how do you find the that value? Minus b over 2a. So minus 24 over 2 times 24. Well, there's your -1/2 again, right? And that's, you know, a function that's decreasing and increasing. I take more time with this in class to, you know, remind people of their rules. You know, so at -1/2, we've got a minimum rate. And so if we looked at 2x plus 1 cubed, it's always increasing. And at -1/2, we got a 0. And if you look at tangents, that's the one that is changing least quickly. A minimum change occurs there. And if we had a different cubic, but still positive a value, that's where the slope is most negative, which therefore is a minimum. Okay, anywhere else, any other tangent, those are increasing, these are decreasing, but that's decreasing the fastest right there. All right, so there are some nice things to talk about in that context. And if we were going to take x cubed plus 12x squared, let's see if I got this desk here, it'll be easier to move. Let's move that. Let's see if I capture everything. Yeah, okay. So, you know, how do you put these in graphing form? Well, the tangent to the point of inflection is the end of the graphic. But we already have a structure here that I just got to fill in 1, 2, 3, 4 values. And we already know -1/2. So we're going to say +1/2, +1/2. All right, so now I'm down to 2. So actually I only had 3 things to find. Had to put one of them, both locations. You can do this algebraically, the graphing form for completing the cube, and you'll find that C minus 3AH squared, where H is the value minus B over 3A, which we know is -1/2. So what do we have here? We have C was 6, minus 3, A was 8, and -1/2 squared is 1/4. Well, that's not too bad, right? So that's 6 minus 6, which is 0. And by the way, this perfect cube, let me get this in my hand again. Put it back there. There was the graph, right? This was the graph of, right? And it's flat there. That's the point of inflection. And yes, it's flat there. So we could have found that out by, so where am I now? So this is actually 0. Oh, God, help us. I would have liked to have had a different number, but that's 0. And now we just have to find out the value that we get when we put -1/2 in. And I think we can see -1/2. Well, you have to put it in here, right? And so -1/2, either a 0 gets a 1 and we put a 0 in here. It might be easier to do that. So a 0 in here is 1/2 cubed, which is 1/8. 1/8 times 8 is 1. Did I run into a glitch here? Let's make sure. C minus 3A H squared. Yeah, it's still 0. I've got hung up here on something, and I'm not sure what. All right, so 0 gets you 1. Well, -1/2 should get us 0, right? And if we put -1/2 in here, we do get 0. So comes back to that. Late in the day, my brain seems to have gone somewhere hiding. Anyway, I'm gonna leave that because I'm lost in my own brain right now. I got my nursing home application in. They're gonna take me in at some point. It's also probably nice to just take something very simple, x cubed, x squared cubed, which is x to the 6th. Kids all know at this stage 6x to the 5th is the derivative. And if you take the derivative of x squared, 2x times 3 times x squared, you get the same answer, right? You got 2x times 3x to the 4th. And so what do we got? We got our 6x to the 5th using the chain. So from a mechanical standpoint, that can be somewhat helpful. And so then at the end of that long discussion, you got to present things. Hey, if you're a student, your first crack at a derivative. And I think the derivative of 3x plus 7 makes more sense by putting that rate of change first. The sign, the derivative of sine is cosine. And then you would have to figure out where you were. Let's say we wanted y prime of 5. You know, how is this linear function changing at 5? At 3 to 1. How is the cosine function? What's the value of the cosine function at 5? Well, really, you're looking at where the cosine is at 22. That's probably a good time to have the kids, you know, graph this function. See if they can graph that function, have that discussion. All right, and not easy, right? Really makes kids think. And you might have to say, hey, well, okay, tell me what comes out of the sine of 3x plus 7. Comes out of that. Hopefully you get to the point where you talk about maximum 1, minimum -1. All right, and so what if you square that? Well, negatives become what? Positive. And I don't think you get bigger than 1. And then maybe you get on Desmos and you show them that it looks like this. You know, it's good little practice to just get a sense of that, because a lot of people don't even know what in your class are going to know what that 22 stands for. And so you might have to, you know, talk about unit circle, radius of 1. And if you use that as a ruler, then how many of those does it take to get all the way around? And hopefully somebody says 6.28. All right, so you got all these review questions coming in here by simply having somebody do this. Now, the way that the typical process would occur is you would take the derivative of squaring, which is 2 times whatever is in the rest of the problem. And that would be to the 1. And then you take the derivative of sine, which is cosine of 3x plus 7. And then you take the derivative of 3x plus 7. It's the same thing, right? But I think if we did the chain rule in terms of the way we find position in the order of operations that allows you to find position, why not mimic it with each step, the rate of each of those evaluations? I guess that to me is going to be an easier way. Not that I'm not teaching calc much anymore, but if I was to be teaching calc, if I were to be teaching calc, I would be doing it in that order. Now I got to go back and find out where I got lost in my graphing form. Let me just do it the way I would have normally done it, just for my own benefit. Let me just give you an idea of a hand problem with a different point of inflection. I think it would be useful since you might not be looking at that graphing form for cubics. So let me just do a quick one here, just to show folks that you can get an idea of how to graph. Say 2x cubed, let's make this minus 6x squared minus 10x plus 5. All right, so you really want to, here's a quick sketch. You're at 5 for a y-intercept. We'll call that 5. I might be off the board with this thing. Going down at 10 to 1. Going down even faster with that term, but eventually turning around, coming back up. So we got something that looks like that. All right, so let's dive into it better. 2x minus b, 6 over 6, x equals 1, so minus 1, that's nice. 1's going to be a real easy number. C minus 3ah squared. So the point of inflection starts at 1, so it's probably in here or in here somewhere. Oh, this is a cubic, sorry, I'm so used to doing squares. All right, it's cubic, so C is minus 10, minus 3, A is 2, and H is 1 squared, so we got ourselves minus 10, minus 6, so minus 16. We're going down at 16 to 1, x minus 1, then we drop a 1 in, and we get 2 minus 6 minus 10 plus 5, and that's going to be the y value of the point of inflection. That looks to be negative 9, I think. So if you multiply this out, you should get back to where you were. But now we have ourselves a much better way of graphing this. So we're going to start at 1, negative 9. We'll call that 1, negative 9. Let's go there. It's not the best. We know the y-intercept is 5, and we're still going down. So we actually have something that looks like this. There's the point of inflection and symmetry with the max and mins, except for change of sign. And you can find those pretty easily. So the x value here would be 1 minus the square root of negative 16. No, that'd be positive 16, because you got to change the sign. All over 3a, I believe. So I think that's that x value, and this one would be the plus 1 plus the square root of 16/3. I did some work on that, lost it because Maple computer programmer went from iteration 8 to iteration 32, and I never kept up with it, so all my work got lost. But so you're going down at 16 to 1 right here. And if we do some calculus here, well, let's do some calculus on this. Let's get our derivative, and we can get that tangent, right? We can get that tangent through calculus just to kind of verify that it's true. So there's your 6x squared minus 12x minus 10, and then your y double prime is 12x minus 12. So, you know, when you set that to 0, you get x equals 1, right? So that's highlighted. When you drop a 1 in here, you get 6 minus 12 minus 10, and that's minus 16, by the way. And you always get that 2 to 1 ratio, opposite sign, only at the vertex of the quadratic. And so you've got minus 10, here's minus 10 going down at 12 to 1, and then it's, you know, it's a square, and so there's a minimum value here, and that minimum value occurs at 1, negative 16. All right, and you know, decreasing, increasing, so concave down, concave up. A lot of things to hit when you don't get stuck just doing, you know, 20 chain rule problems in a row. activate the brain, try to come in from all different angles, geometric, numerical. So I'm still got to go back. Well, I can't now. I erased it. Well, I got the video. So if I want to, I can. Maybe I didn't make any mistake with that. But anyway, wanted to clear up some of these topics here. And so, the rest of the graphing form. So if you want to get graphing form, maybe calculus is easier. Getting this tangent and then simply taking the A term, writing that. And at least you can see what the graph looks like without a calculator. All right. And a rough estimate here, 16 divided by 3, 5-ish. Square root of 5, square root of 5, maybe 2.5, 2 1/3, 2 2/3, I don't know. But it gives you a little rough estimate, and it's good to have some understanding of some values. So that may not have been the best video ever made, but a lot of ideas to think about, and it'd be interesting to see if anybody tries teaching the chain rule in the same order that we evaluate functions in, rather than outside in, inside out. Worth trying. Bye-bye.